Hello there, and welcome to Network Wednesday here on Answer Everywhere. Today we're looking at the source code for eBPF, the kernel thingy that lets you put user space programs into the kernel in a way that's not so terrifying and scary. eBPF has been around for a long time. I think it first came out maybe around 2016 or so, but we're starting to hear more and more about it, especially related to cloud stuff, like Kubernetes network plugins and that sort of things. I don't have a great sense of what's going on. My mental model is basically we get to push user space programs into the kernel. The kernel is going to verify them in some way to make sure that they're not that there's some bound on their complexity and a bound on the damage they can do. And then the kernel is going to run those programs on our behalf. And in that way, we'll be able to extend the behavior of the kernel to add things like fancy networking support or observability, additional security, observability and enforcement, and those sorts of things. And I see some people in the chat are just saying hi. Hello, everyone. Hi, Jamal. Hi, Sinnerman. Sinnerman, how's it going? So here's a let me maybe pop this off for a second so we can look at this diagram, which is pretty large. And here's the kernel, and we've got the kernel runtime with the B, which I am assuming means eBPF. And there's a verifier, some sort of thing that's going to look at programs and verify them, and a just-in-time compiler, an OS runtime, and some maps. I'm not sure what kind of maps, but possibly associating. There's going to be some logic that like matches different calls to different programs to run, and maybe that's what the maps do. And then a helper API, which is presumably just kind of the surface by which you modify and juggle around with eBPF programs. And applications, they list tracing, profiling, and monitoring. These are classic like cross-cutting concerns that you would have in a data center type environment. And the idea is that we're going to push them into the kernel. So why push them into the kernel? Well, usually because it's faster. You don't have to context switch as much if the kernel is running your programs for you. There's also, in some cases, things that the kernel is able to see that you're not able to see. And so that's where some of the observability, I think, and profiling come in. And then there's going to be some massive amount of tooling to kind of make whatever system is actually in the kernel usable by mortals who are not kernel hackers. And we're mostly going to ignore that level. I think where I want to get today is I'd really like to see the verifier and the just-in-time compiler. And I'd like to have a sense also of how the kernel decides to run which eBPF program. And I think that's about the best that we can do in a few hours, not having seen this code base before. So let's see what we can do. Oh, and before I begin, I officially have 5,000 subscribers, which is insane to me. Thank you for everyone who's subscribed. Thank you for everyone who's watched the videos and commented. It means a ton. This has been unexpectedly wild ride for me, and I really appreciate it. And I'll pop back the chat in here. All right. So I have no idea where the eBPF code is. So let's see if we can find it. My guess is it's going to be in some version of net. Although I'm not sure if it's this particular net one. Maybe one thing we can do is grep eBPF in the kernel, which I don't think GitHub will want me to do. I also have whatever that's also GitHub. I previously had the like cgit interface. But let's see if GitHub will let me search for eBPF. Can't find anything. Maybe some commits. Add user space API. Act eBPF. I think I looked at this before. Prepare BPF trampolines. Maybe this is stuff. Let's see if it touches any files that. We have BPF JIT comp, maybe JIT compiler. This looks promising. How do I get to the actual file? GitHub, view file. Okay. But I'm not sure I want SC390. Maybe I want to look at Arch x86. Unless there's a 64 version. ARM 64? No. ARM? I guess x86. Let's see if they have a JIT thingy. You have a BPF JIT comp, and then the N32. So I'm going to assume the one without the 32 is the 64-bit version. And let's just see if this is the sort of thing that we want to be looking at. BPF JIT compiler. I think I read somewhere that in the Linux world, the Linux kernel people refer to eBPF as BPF. And so I'm not sure this is related, but this is from 2011 to 2013. So maybe this is not the thing that I necessarily want. What do you think? Let's take a look. Let's try grepping the code. Maybe eBPF. We get lots of hits. Lots of stuff in BPF compiler. That's ARM 64. Spark, MIPS. Maybe we'll look for x86. And just to get the color right, let me add another eBPF. I don't want binaries. How do I not? Maybe something like that. Okay. So there's some stuff. We have x86 kernel CPU bugs. We have this JIT compiler, which I think is the file we're looking at. And what is cBPF? I'm not sure. Let's try eBPF cBPF. Is that what it was? eBPF is the extended for yeah. Thanks, Jamal. I'm also seeing people say that that's no longer true, which I suspect is the case. I think it's probably how it started. Do Metasploit in the future. I'd consider looking at Metasploit, sure. Maybe leave a comment somewhere if you don't mind, George. Okay, so let's look at what Wikipedia says here. It can it could run sandbox programs. Yeah. Evolution from classic BPF. I think this is what Jamal is saying. It was built on top of the Berkeley packet filter cBPF. Okay, so that's what cBPF is. Maybe classic BPF. Another user mode interpreter is uBPF, which supports JIT and eBPF without cBPF. I don't still know it. Okay, classic. Okay, yeah, great. This is what I wanted to know. Since kernel version 3.19, eBPF filters can be attached to sockets. And since 4.1 to traffic control classifiers for the ingress and egress networking data path. The original and obsolete version has been retroactively renamed to classic BPF, cBPF. Nowadays, the Linux kernel runs eBPF only, and loaded cBPF bytecode is transparently translated into an eBPF representation in the kernel before program execution. Okay, so this is kind of similar to what we saw with IP tables, right? So IP tables is the kind of older, classic, obsolete version, and has been replaced by something like net tables. I don't think that quite sounds right, but something with net in the prefix. NF tables, maybe. And so that's what happened. And so based on what that Wikipedia article just said, I'm going to assume that whenever I see BPF in the kernel code, since eBPF is the only thing that supposedly the kernel is doing, I'm going to guess that BPF typically means eBPF. And that CBPF means classic. Hi MSA. Okay, so here's the x86 .NET BPF JIT compiler. And I have no idea what we're going to see. So I don't know what BPF, whatchamacallit, like bytecode looks like. I think it's some sort of a VM that's running bytecode. You give it some program that you program probably in a high-level language, and then that gets compiled into bytecode. And somehow you tell the kernel, look at this file and load it. So there should be stuff that like builds maybe some sort of abstract syntax tree, analyzes the code, or maybe it just has the bytecode version and it's just doing some sort of a check on which kind of bytecode operations you can do. I really have no idea. So let's maybe see what's going on in the JIT. But actually, more than the JIT, what I'd really like to see is the verifier. So perhaps before we get to the JIT, let's see if we can find something like verif. I think the kernel uses a lot of short names. Hey, look at this, kernel/bpf/verifier. Yeah, I think I want to see this first before the JIT. I'm not positive. BPF verifier. Kernel. Yeah, I have to find kernel first. And in kernel, there's a bunch of just BPF stuff. cgroup storage, BPF iter. Don't know what that is. Iterator, local storage. I think there is local storage in BPF. And struct ops LSM. That should be Linux security module. And task storage. I'm going to open all of these. But before I do, yeah, okay, I have the JIT compiler already. So cgroup storage, inode storage. We're going to grab all of these files. But I haven't seen the verifier. This should be a BPF directory, which is where I am. Oh, okay. I thought I was in the kernel directory. All right, so all of this is BPF stuff. Okay, including trampoline, which we might as well look at. syscall, I guess I'm going to ignore ring buffer and stack map. I'll open stack map just because that diagram we looked up had a map. So maybe that's the map. I'm going to guess it's not. But we have mmap unlock work. Map and map. This looks more promising as a map. Map and map. LPM try. This is going to be some sort of try data structure, I assume. And so maybe that's not so important to look at. Inode. I'm going to guess since we're in BPF, this is some sort of BPF inode interface or whatever. Helpers. This might be the helper API that we saw. Disassemble. Hash tab. Dispatcher. I want to see the dispatcher. I want to see disassemble. Dev map is probably device map. Core might be important. Everyone loves C groups, so we'll look at C groups, and I have no idea what btf.c is. And so just so we don't have like a letdown after looking at a bunch of cool stuff, let's verify that btf.c is something at least mildly interesting. The BPF type format, I think we looked at this before, maybe in the Linux kernel video, is the metadata format which describes the data types of a BPF program /map. Hence, it basically focuses on the C programming language, which the modern BPF is primarily using. There's some stuff about ELF. Is this important? This might be important. BTF show. I guess I'm going to close this, and if it seems like we want to know what's in here, we can revisit it, I suppose, if we remember. The metadata format. It describes the data types. I guess I do kind of want to know that. All right, well, that's going to be at the end. I'm not sure if that's where it should be. Here's the JIT compiler. But I think what I really want first is the verifier, which is now somehow buried after the B stuff. Here's a trampoline. Okay, so let's look at the verifier. George, with respect to stuff like Metasploit, and I think you were maybe also asking about something else in one of the comments. My only rule is that I want to be careful about. I don't want to look at any code that is in violation of like terms of services or whatever. Or like copyright. I have no idea what's in Metasploit. It seems possible that some of the exploits might be from might violate some contract terms of service stuff. I don't want to give any lawyers any reason to like come after my channel or what I'm doing. So with that caveat, I'll probably take a look at Metasploit offline and verify that it seems okay to look at. But that's my only caveat. Or if like I'm not going to read like leaked. Sometimes source code has been leaked from a company. I'm not going to read that sort of stuff. And then stuff like reverse engineering might be a corner case. So just trying to give some parameters. If I so far I've not said no to anything, I don't think. But I may at some point say no to something like that, and I don't want anyone to feel like I'm singling them out or anything. That's kind of just a general rule I have. But I suspect that Metasploit should be fine. All right, so here's the verifier. Okay, so imports look totally cool, except we've got the verifier header, which we should, I think, look at before. So let's see. Where do I have to go? I have to go to like probably the include directory somewhere. Include eBPF, include kernel. Unless the verifier header is in the same place. Let's try find. What? Oh, .h. Okay. Slash include slash Linux slash BPF verifier. Okay, so I need to find the Linux directory. So include Linux. Okay, they're going to truncate the directory. And then was there a BPF folder? No, it's just a file. And we can actually have a bunch of headers. And so you know what? I'm going to open these headers as well. I think in a lot of cases with stuff like the kernel, especially when you don't know what you're doing, like I don't know what I'm doing, the headers are the right level of granularity because you get the API and you don't have to understand as much about the implementation. A lot of figuring out what you're doing is knowing what to ignore. And the more stuff you have to ignore, the more cognitive overhead there is in figuring that out. Okay, so BPF verifier, here's the header. And we include the BPF header and the BTF header and filter. Okay, so you've got some maximum offset stuff. Permitted when resolving memory accesses. Okay, we've got liveness marks. I don't know. Used for registers and spilled registers in stack slots. Read marks propagate upward until they find a write mark. They record one of the state's descendants read this register. and therefore the register is relevant for states equal checks. Write marks collect downwards and do not propagate. They record that the straight line code that reads the state from its parent wrote this register, and therefore that reads propagated from the state or its descendants should not propagate to its parent. A state with a write mark can receive read marks, it just won't propagate them to its parent. Since this write mark is a property, not of the state, but of the link between it and its parents. See mark reg and mark stack slot read. I don't know what this means, but we will learn about it. And I believe that I saw somewhere that eBPF is basically what's called a register machine, and in particular is a risk register machine. Let's verify this. Collabora. So this is saying eBPF is a risk register machine with a total of 11 64-bit registers. What does this link to? Hey, this links to the BPF header. I think this is the first time we've seen an outside blog linked to the same source code we're looking at. So that's kind of cool. And so here are the registers. And there are 1, 2, oh, well, they're numbered 0 to 10. Okay, so there are 11 of them. And they're just called BPF register number. And oh, we get info about them. So R0 stores the return values, both for the function calls and the current program execute. R1 to R5 are used as function call parameters, or function call arguments. Upon program start, R1 contains the context argument pointer. R6 to R9 get preserved between kernel calls. So I guess you can use them to save state somehow. But you only get 3 of them. I don't know what can go in a register. I think I just closed the file that it pointed to. Yeah, I'm not sure. We'll try to figure out how much stuff you can stuff into a register. I would guess about like a word, right? Or half a word. I don't know how assembly works. R10, read-only pointer to the per eBPF program, 512 byte stack. Oh, 64-bit register. So you can store 64. You can store 64 bits in them. The eBPF program type supplied at load time determines exactly what subset of the kernel functions are available for calling, etc. So this is actually super helpful. I'm going to bookmark this, and I might. It's talking about all of the different code. But I also want to take a look at maybe Wikipedia has a risk machine. Maybe just reduced instruction set computer. So there's some like standard stack diagram. What about just reduced instruction set? I'm not sure that I see it. Oh, maybe it's a maybe it's in register machine. Yeah, I'm not sure. What about risk? Fetch instruction, load, memory. Classic risk pipeline. Here we go. I'm not sure if this is the risk pipeline that's used by the eBPF machine, but this is just maybe just something we'll have in mind. So chat will go off to the side for now. So IF is first we have this instruction fetch, and I guess this, as we're executing, we're putting things on the stack and then we pop them off the stack. So first we're going to fetch an instruction, then decode the instruction, execute. Mem is memory access. WB is register write back. So I guess this is kind of like a return value sort of thing. And then what do we do? we have lost. So we're down here. So we've lost instruction fetch. And then I guess we lose things from the, I want to say first in, last out, but it's actually called what? Last LIFO? Something like that. But we're losing the first things that we put on. And then at the end, we just get the write back. Okay, so that's kind of how I'm going to imagine things are going until I know otherwise. And I think I have another copy of this BPF header open, so I'll ignore that. All right, and so I was looking at this thing. This is something about liveness marks and registers and spilled registers. I'm going to see if ChatGPT is willing to explain this to me. And just for fun, I'm going to ask it if it can explain it like a Ninja Turtle. Okay. All right. So it says Cowabunga, dude. So this like paragraph is talking about these things called liveness marks for registers and spilled regs in stack slots. When you read something, that mark goes up until it finds a write mark. That read mark means that, yeah, but this is not really helping. On the other hand, the write mark collects downwards and don't spread. So we have these, so we've got these liveness marks for registers. Okay. So when you read something, that mark goes up until it finds a mark. But what does it mean to go up? That mark, that read mark means that one of the state's descendants read the register. Okay. So we've got this kind of stack thing going. And if you see this mark, that means somewhere, one of my descendants left it, but maybe that descendant is like gone or no longer here. On the other hand, write marks collect downwards and don't spread out. They record that the straight line, which means that reads that come from the state or its descendants shouldn't spread to its parent. Okay. That ChatGPT, I'm glad you added the Cowabunga, dude, but that was mostly just regurgitating what was said. Maybe I'll try. Can you explain it like I'm 5? Yeah, so it's talking about some marks that we put on things called registers and stack slots. When we read something, we mark it to say we looked at it. When we write something, we mark it to say that we changed it. When we read something, the mark goes up. But I still don't know it goes up. All right, thanks, ChatGPT. All right. Okay, so let's take a look at these things. And these are just some enum liveness. So like live non, live read 32, read 36. Register was read, so we're sensitive to initial value. Read 64, likewise, but for full 64 content matters. And then live read is the same as live read 32 or live read live read 64. And then we've got written and done. Okay, so those are just some enum. And we'll try to figure out where the liveness stuff is being used, because I don't have a sense of, it seems to be something to do with the stack and propagating up and propagating down. But I'm having a trouble, I guess. I don't know, if I were building this machine, I don't know what I would be doing with those things, I guess. All right. So here's some lock. The lock has some void pointer. For every register representing a map value or allocated object pointer, we consider the tuple of pointer ID for them to be unique in verifier context and consider them to not alias each other for the purposes of tracking lock state. Okay, so the pointer can be either a reg map pointer or a reg BTF. If pointer is null, there's no active lock held. Okay, so that's some locking stuff. And we've got register state, I guess, so which is a struct, BPF register type. And the ordering of fields matters, see states equals. And we've got this 32 bits thing, which is the fixed part of the pointer offset. So I guess, right? So that's, I guess, half of the 64-bit stuff for the pointer at least. I don't know if, I think that's different from what's being stored in the register. And then we have a union of some stuff, a range, a BPF map pointer, a map with a map UID. So this is like a pointer and a name, essentially, thinking of the UID as a name. or it might be this BTF stuff. I guess that's like the type metadata. Whatever this is, something about mem size and dynamic pointer ID for dynamic pointer slices, maybe for pointer to mem or pointer to mem or null. And then we have, I think we're still in the enum, right? Another thing this enum could be is a combination of a BPF dynamic pointer type and a first slot for dynamic pointer stack slots. And then something about max sizes from any of the above. Then a subprogram number, which is a pointer to a function. And I guess the idea is that since this is called subprogram, this is like a pointer to the next thing that's supposed to execute in this program. And then for scalar types, we have var off. This represents our knowledge of the actual value. For pointer types, this represents the variable part of the offset from the pointed to object and is shared with all BPF reg states with the same ID as us. All right. And we've got a bunch of max value, min value, which is used to determine if any memory access using this register will result in bad access. Okay, so this is just, we've got some concept, I guess, somewhere of a chunk of memory that we're letting this program access, and we're making sure that it doesn't access outside of that area. So you can't have your eBPF program like try to read the TLS keys of some web server that's running in the same like cloud environment or host or whatever. We have an ID, which has different meanings depending whether it's a pointer to whether our pointer is a pointer to a packet or map or null or pointer to socket. I don't think we've seen yet. This is used to share which pointers retain the same reference to the socket. Okay, so this is a little bit like ref counting to determine proper reference freeing. For stack slots that are dynamic pointers, this is used to track references to dynamic pointer to determine proper reference freeing. Okay. It seems to be mostly used for freeing for all of the stuff. And what is this down here? Ref object ID can also be a bunch of stuff. Pointer to socket and pointer to TCP sock could be a pointer returned from a pointer cast helper. BPF sock full sock. In BPF TCP sock, consider the following where SK is a reference counted pointer returned. Okay, so it's going to be something that I'm not going to dig into this level of detail, at least not yet. And we've got some parent, a parentage chain for the liveness checking. So I guess this is all used for liveness checking. And then a frame number. Inside the callee, two registers can be both pointer to stack, like R1 equals FP minus 8 and R2 equals FP minus 8. But one of them points to this function stack while another to the caller stack. To differentiate them from frame number, frame number is used, which is an index to BPF verifier state frame array pointing to the BPF function state. Okay. This frame number somehow differentiates two things in the callee, two registers that might otherwise be confused somehow. And then we have subreg def, subregister something, tracks subreg definition. The stored value is in the whatever INSN index of the writing INSN. I don't know what an INSN is, instruction maybe. This is safe because the subreg def is used when any instruction patching, which only happens after the main verification finished. And then precise. If not precise and scalar value, then the min max stuff don't affect safety. Okay. Seems like if you can overwrite precise somehow, you can bypass the safety checks. I'm not sure what the safety, yeah. Okay, just a thought. All right, so we have a BPF stack slot type, invalid, spill, miscellaneous, 0, dynamic pointer. A register spilled into the stack. I don't know what it means to spill into the stack. Does it mean we've just like copied the data? And we might have nothing stored in the slot, and the BPF program might have written stuff, or it wrote a constant 0. Let's look at stack spill. Maybe Wikipedia knows. Spilled to memory. On stack machines, temporary values often get spilled into memory, whereas on machines with many registers, these temps usually remain in registers. What does it mean to be spilled? I think it just means moved to memory, right? Okay, let's assume that's the case. Okay, and we've got some struct to track stack state and a BPF reference state. Track each reference created with a unique ID, even if the same instruction creates the reference multiple times, e.g. via call. And some instruction index and a callback reference. Okay, so I guess let's look at the rest of this. Instruction, where the allocation of this reference occurred. So this keeps track of where this reference was defined. And then a callback reference, it says there can be a case like main frame 0, callback frame 1, function frame 3, callback frame 4. Here for frame 4, if callback ref just stored Boolean, it would be impossible to distinguish nested callback refs. Hence, store the frame number and compare that to the callback ref and check reference leak when exiting a callback function. So when we do callbacks, we check the frame number to see how nested we are, more or less. Okay, so here's the state of the program, type of all registers and stack info. So this is kind of the machine, the machine state part of the virtual machine, perhaps. Let's find out. So we've got the struct of BPF state register, BPF reg state, which is register, like an array of registers of max BPF register. Do we have, let's see if we can find this. Is this 11? I'm not sure. Where is it, about 250? Let's try, I'm just curious to see what the value of max BPF register is. I already have a terminal. Something like that. What about equals? Define. Open the BPF header in Emacs so you don't get the tab all confused all the time. All right, let's see what we got. Okay, and so just set the underscore max BPF reg, and max BPF reg, I guess, is part of this enum, right? So it's whatever, it's 11. Right? So the enum value of this should be 0, 1, 2, 3. Yeah, okay. I think it's just set to be 11. Where did my thing go? Oh, this is the wrong tab, wrong browser tab. Here you go. All right. So this is the state of the program. BPF function state is what it's called. It's a struct. And we've got 11 registers, an array of 11 registers. We keep the index of the call site that called into this function. We keep the frame number, which is the stack frame number of this function state from the point of view of the enclosing BPF verifier state. 0 is the main function, and 1 is the first callee. All right. And then we have a subprogram number, which is the index within the subprogram info. 0 is the main subprogram. Then async entry count. Every BPF timer start will increment async entry count. It's used to distinguish void foo void with a infinite for loop, and void foo void BPF timer set callback, comma, foo. All right. So I guess we want to know maybe how many times we've been called to know if we're in like an infinite loop. I'm not sure. And we've got some in whether we're keeping track of a Boolean about whether we're in the callback function, callback return range, which is a T number. I don't know what a T number is. And then we've got whether we're in an async callback function. And then the following field should be last. See copy func state, acquired references, a pointer to some reference states, an allocated stack, which is an int. Maybe that's telling us how much space or something we've allocated or how many frames. And then BPF stack state, which is a pointer to stack. Is this stack state? This is function state. Do we see stack state? Here's reference state. Oh, stack state is this. It just has this build pointer thing and a slot type. All right. Max number of call frames is 8. Maximum number of register states that can exist at once is BPF ID map size, which is this thing. I don't know if I know what all these variables are. And then we have a BPF verifier state. We have this func state frame of max call frames for use for call stack tracing, I guess, and the verifier state parent. So the parent implies that there's some sort of tree structure to this verifier, I would assume, or maybe it's just the stack parent, right? So we've got this stack and we've got stack frames. So actually, scratch what I just said. I guess parent must mean stack parent, which is kind of like a tree or a graph of some sort. And then we've got branches. Branches field is the number of branches left to explore. Okay, so we can branch. So we're kind of like a tree. 0 is all possible paths from the state reached BPF exit or were safely pruned. So, okay, so let's left to explore. So if branches is 0, we've explored all the things. And not only have we explored all the things, but they've reached BPF exit, which might be the same thing as exploring all. So then we're not going to like have a non-terminating program, I assume, is what BPF exit is. You want to avoid the, the possibility that something's going to, that your BPF program is going to run indefinitely. So 1 means at least 1 path is to be explored. 2 is at least 2. I think that's generally what numbers mean. The state is an immediate parent of 2 children. Okay. So for 2, this means this state is an immediate parent of 2 children. And I guess those children might have other children. So these are the branches left to explore rather than the total number of nodes left to explore. 1 is fall through branch with branches equal 1, and another state is pushed into stack, blah, blah, also with branches equal the parent is 8. I think this is now going through examples, which is useful. Which I guess we're not going to look. Yeah, maybe we'll look at. But what we're seeing is that, like, as you push and pop stuff, the numbers change. So I guess 2 goes to 1 first if pushed into the stack. And then we're 1 again. I'm not sure how we got to 2 here, but then 2 goes to 1 second if pushed to the stack. And then we get BPF exit. Yeah. And then we're going to, I guess, somehow count down to 2. I think this is just walking through some sort of graph traversal. If isState visited sees a state with branches greater than 0, it means that there is a loop. Okay. So isState visited should be some sort of function that takes some state and returns a Boolean. And if it sees a state with branches bigger than 0, it means there's a loop. I'm not sure why. Why doesn't it just mean we're not necessarily finished looking at stuff? But if such state is exactly equal to the current state, it's an infinite loop. Interesting. Note states equal checks for states equivalency. So two states being states equal does not mean infinite loop. The exact comparison is provided by states maybe looping function. It's a stronger pre-check and much faster than states equal. The algorithm may not find all possible infinite loops, or loop iteration count may be too high. Okay, so we're going to try... we want to have bounded loops. We don't want to just execute arbitrary, like Turing complete functions in BPF. And this is, I guess, the stuff that's going to do it. We're somehow going to have this branches thing. And this is the condition. If state visited sees branches with bigger than 1, then there's a loop. And if the state is exactly equal to the current state, it's an infinite loop. And that's presumably bad. So let's go. So this is about line 308. Let's go look through the rest of the file and then maybe come back to this walkthrough thing once we have a better sense of what's going on in the structs and the algorithms and stuff. So we have branches in instruction, index, and current frame. And then we, what is this? This struct is the BPF verifier state. And then we have some lock stuff, speculative. Maybe that's like speculative branch execution. And another lock thing. I don't know what RCU is. But I guess it probably doesn't matter right now. And then we have the first and last index of this verifier state. And then we keep track of a jump history recorded from the first to last. Backtracking is used to go from the last to the first. For most states, jump history count is 0 to 3. For loops can go up to around 40. And a jump history is a BPF index pair. We've got a jump history count, which is a U32. We can get spilled registers, which we're going to ignore. BPF for each reg in VF in vstate. It says invoke __ express over registers in __ VST setting. Well, I'll just call that _ state and _ reg. I don't know if that's interesting, but we're going to move along. We're still in the header, right? Yeah. But I think we're close to the bottom. We have a BPF verifier state list, a linked list of verifier states used to prune search. Right, so we've got the state and the next. So it's just a linked list of the states. BPF loop inline state, initialized, fit for inline, and some callback program number. So initialize is set to true on first entry. Fit for inline is true if callback function is the same at each call and flags are always 0. And subprogram number is valid when fit for inline is true. So I'm wondering if something like this, the inlining is used in the just-in-time compilation. Not sure. And then we have possible states for ALU state member. Sanitized source, sanitized destination, negative value, non-pointer, immediate, and sanitize. I don't know what ALU is. I don't think we've come across that yet. ALU, let's maybe look that up. Maybe ALU is a more general thing. Here's some Go implementation of eBPF assembly. Source of ALU branch operations. Arithmetic logic unit, or maybe arithmetic logic unit. In computing, an arithmetic logic unit, ALU, is a combinatorial digital circuit that performs arithmetic and bitwise operations on integer binary numbers. This is in contrast to a floating point unit, FPU, which operates on floating point numbers. It is a fundamental building block of many types of computing circuits, including the central processing unit of computers, FPUs, and graphics processing units. Okay, so this is some, ALU is, I don't think of it as like some sort of chip, some sort of hardware thingy that's used for arithmetic. And this is somehow recording values about them. Here's the BPF instruction auxiliary data. And it's got pointer type for load store instructions, pointer poison values for maps, IMM fields, I'm not sure what that is. Okay, so you know, auxiliary data. This doesn't look so fundamental. Storage get func atomic. Same is storage get with atomic memory allocation. We have max use maps is 64, and max use BTFS is 64. That's the max number of maps you can access by a single program. The temp log size is 1024. And then we have a verifier log. I guess this is used by the verifier as it's verifying to keep track of stuff. Or maybe it's just used for printing it out, because we've got a log level, log size, and we're keeping track of how much is used in a buffer, I guess, which is called user. So maybe that's something, maybe that's logging going to user space, is my guess. And then we've got an inline bool, BPF verifier log full. That's just log stuff. We're going to ignore logging stuff. Max subprograms is 256. So this is, I guess, a bound on whatever a subprogram is in eBPF. So subprogram info has start linfo index, the index to the main program aux linfo. Line info, I don't know. I don't know what L is. The subprogram info has stack depth, whether it has a tail. Something on OBS started flashing red, and then it said I was disconnected. So if anyone's in the chat, please let me know. And in the other window, I'm going to reopen the chat to see if I'm still at the same place. So it seems like I'm still streaming to the same place. But give me a second. Okay. So, all right, that seems to be okay. Sorry if anyone was kicked off. I don't know how it works when that happens. Then we have some environment for the BPF verifier. A single container for all structs, one verifier env per BPF check call. Is this a big struct? It's a pretty big struct. We've got the instruction index, a previous instruction index, a BPF program to be verified, BPF verifier ops, maybe operations or options. The head, which is a BPF stack element, a stack of verifier states to be processed. A stack size, I guess whether to strict align, a pointer to the current verifier state, a pointer to pointers of explored states for search pruning optimizations, a free list, used maps, used BTFS, a map count, a BTF count, whatever ID gen is, something about exploring ALU limits, something about pointer leaks, uninit stack, maybe uninitialized stack, allow uninit stack, BPF capable. I don't know what that means. Maybe it's possible to not be BPF capable. Bypass spec v1, bypass spec v4. I'm not sure what this means. Maybe there's a bypass spec. Scene direct write, RCU tag supported, BPF verifier log, auxiliary data, previous line info, subprog info, ID map scratch. This is, and then some config, which is the state, the stack, and the current stack. And then keeping track of the pass count, the subprogram count, the number of instructions analyzed by the verifier, so like instructions processed, previous instructions processed, then jumps processed, total verification time, max states per instruction, total states and peak states, and the longest mark read walk. Then we have a bit mask to keep track of whether a register has been accessed since the last time the function state was printed. Okay. So there's a lot there. I still don't have a sense of like what the verifier is actually doing. It's obviously something about stacks, and we're going to walk the stack. We're going to check for loops. We're going to check for memory accesses. And I guess that maybe by the structure of the like bytecode stuff itself, there are also additional limitations that maybe aren't visible to the verifier directly. They're just more in the way that the thing has been designed, what a programmer can try to do. All right. We've got offload verifier pref, offload finalize, etc. Trampoline compute key. This lives here instead of bpf.h because it needs to dereference tgt program. Trampoline unpack key. We can bpf check attach target, which takes a log, a program, a target program, a BTF ID, and attach target info. I don't know what that does, but I guess you can attach the target program maybe to the other program. And trusted modifiers. BPF program check recursive. So you're going to pass it a BPF program, or a pointer to one rather, and then we're going to switch on resolve program type. And if it's a tracing program, we're going to return program expected attach type not equal to BPF trace iter. I don't know what that means. If it's a BPF program type struct opts or type LSM, we'll return false, otherwise return true. Check recur, maybe check recursion. And for whatever ops is in LSM, maybe ops is observability. I'm not sure. See if we can find out what this is. BPF struct ops. Oh, you got to define. Something about socks. That doesn't sound right. Define BPF struct types name. Let's just try an internet search. Introduce BPF struct ops. This series introduces BPF struct ops as an infra to allow implementing some specific kernels function pointers in BPF. What does it do? I'm not sure what it does. Maybe like eBPF program types. a tour of program types. This looks promising. Some Oracle blog post. Okay, so there's some enum, I guess. But sock ops, maybe? I don't know. Okay, so that's the verifier header. Let's go back up to how it was doing this walkthrough example. Is this where it was? Branches? I think it's branches is what I want. Okay. So the number of branches left to explore. Yeah. So where's the extent? So one is fall through branch with branches equals 1, and another state is pushed into the stack to be explored later. Okay, so we're at branches equal 1, and we're going to push another state onto the stack, also with 1 branch. The parent of the state has branches equal 1. I guess maybe the parent of the state pushed onto the stack, or the parent of some other state. I'm not sure. The verifier state tree connected via parent pointer looks like this: 1, 1, 2 to 1. First if pushed onto the stack. Are these like the stack levels? First there's a 1 and then there's another 1. And then there's a 2 to 1. I'm not sure what this means, what the 2, 1 means. And then 1, then 2 to 1, second if pushed onto the stack. 1, 1, BPF exit. Once do check reaches BPF exit, it calls update branch counts, and the verifier state tree will look like 1, 1, 2 to 1, first if pushed on the stack, 1, 1, 1 to 1, second if pushed on the stack, 0, 0, 0, BPF exit. After pop stack, the do check will resume at second if. So it'll resume here. So I guess pop stack will get rid of all the 0 stuff. Once do check reaches BPF exit, it calls update branch counts. So update branch counts, I guess it's going to recognize that we're at BPF exit and delete 1 because it knows that whatever this 1 was, I guess we're at the end maybe. And then when we delete the 1, we conclude, I guess, that the second if the 2, we explored one of its branches and now it should be 1. And I guess that's what we see down here. If isState visited sees a state with branches bigger than a 0, okay. And that's the part we saw. All right, so that's the verifier. I still don't have a good sense of what it's doing, but I guess we have more of a sense of what BPF is up to in general, I think. So let's look at the BPF header. We have BPF map ops. Map is a generic key value storage optionally accessible by eBPF programs. Okay, so this is like you get some sort of storage, like a hash table. These are maybe operations. Functions callable from user space via syscall. Okay, so these are, I guess, operations, functions you can call from user space via syscall, as the thing just said. And how am I supposed to read this? So this is maybe a return value. And this is what it takes. Oh no, this is the name of the function. So map alloc check maybe takes some sort of union and returns an int. We can map get next key, update branch, look up and update batch, look up and delete batch. Okay, so this is some key value storage API. Poke, program poke tracking helpers, direct value access helpers. Okay. And then we have the BTF field type. I'm not sure exactly what a field is, but we have spin locks and timers, and maybe, I don't know what K pointer is, but maybe kernel pointer, K pointer unref, K pointer ref, list head and list node, RB root, RB node, maybe red black root, red block node. I'm not sure if these might be user visible. Okay. And a BTF field K pointer has a BTF thingy, the type stuff, a module struct, a destructor, and a BTF ID. So the fact that it has a detour, which I'm guessing is destructor, makes it look like this is kind of an implementation of a programming language, and presumably the language that you program BPF in, so maybe like the BPF bytecode stuff, perhaps. But I'm not sure. Then a BTF field has an offset, a type, and a union of a K pointer and a graph root. And this thing is the graph root. I'm not sure what a field graph would be, but maybe it keeps track of the structure of the fields. A BTF, this really does look like this might be the bytecode, I guess. A BTF record has a count, a field mask, a spin lock at whatever timer off is, and some fields. Maybe timer offset. And then field offs have field off size and a count. And we have this BPF map struct, the first two cache lines with read mostly members of which some are also accessed in fastpath, for example, ops and max entries. This is cache optimized. And I guess the first two elements are accessed in the fast path, so they need to be, I guess, especially fast. So we have the BPF map ops. These are the operations that we saw, which is cache line aligned. And the struct BPF map inner map meta, I guess metadata. We have map type, key size, value size, and a bunch of other stuff. Map extra. This is BTF field off. Oh, no, sorry, this is BPF map. So there's a bunch of stuff related to maps. More things that I think are field offs. I'm assuming off means offset. Here's some ownership stuff. Ownership of program containing map is claimed by the first program that is going to use this map, or by the first program which FD is stored. Which FD? I don't know what FD is stored in the map to make sure that all callers and callees have the same program type, JITted flag, and XDP has frags flag. So this is some stuff, some ownership stuff, which has a lock, a program type, whether it's been just in time compiled, and whatever XDP has frags something, maybe fragments. And then here's BTF field type name, spin lock, timer, unref, and ref. We're going to give the BTF field type. I'm going to get a string. And these two things are, I guess, of type K pointer. Or at least their string is type K pointer. We also have list head and red black nodes. And here's some sizes. We can look up the size of the different fields, I guess. There's some alignment information. We can check whether, I guess, BTF record has a field. You pass it in a record in a field type. And if the record is null, we error out. Otherwise, we take the field mask and we AND it with the type. We're just looking, so the mask just records the type, I guess, whether there's a 1 in that field. And this is just kind of doing that computation. BPF object init, which is void, static inline void. And we've got some offsets and an object. We're going to create the integer I. And if there's no offset, then we're going to return. And then we're going to iterate over the offset count. And we're going to call memset on the object plus the foffs plus the field offset at index I guess initialized to 0, maybe the size of the offset. So I guess this is like zeroing out the data. Let's verify that the second argument to memset is maybe what to fill the function with. Memset, pointer, value, and num. Yeah, okay. So this I'm like 99% sure that what we're looking at is the implementation of like the whatever the programming language used for BPF is, and it's some RISC bytecode machine, right? It's got registers, but it seems to be a thing that has access to maps and essentially structs or classes and fields. It maybe just structs, objects. Is that what it's calling them? I think it's calling them objects. We can check and init map value. DST must be a temporary buffer and should not point to memory that is being used in parallel by a BPF program or a BPF syscall. Okay. By the way, whatever happened to my chat? Did I just destroy it? Here it is. Okay. So we have long mem copy. Mem copy is used with 8-byte aligned pointers, power of 8 size, and forced to use long read writes to try to atomically copy long counters. Best effort only. No barriers here, since it will race with concurrent updates from BPF programs. And then we've got BPF object mem copy. Copy everything in BPF spin lock and BPF timer and K pointers. There could be one of each. Okay. Very cool. All right, what do we have here? Some BPF type flag, maybe null. I guess nullable. Read only ring buffer. Mem points to BPF ring buffer reservation. Mem is in user address space. I guess you can maybe load a program into user space and have your BPF program do stuff with it. I think that might be a pattern I've heard of. Maybe not in the context of BPF. I'm not sure. And then we have mem per CPU and a bunch of stuff. Pointer trusted. What's a trusted pointer? Pointer was passed from the kernel in a trusted context and may be passed to kf trusted args k function. Confusingly, this is not the opposite of pointer untrusted above. All right. Cool. And then we have BPF argument type, function argument constraints. Arg don't care, unused argument in helper function. And then the following constraints are used to prototype BPF map lookup, update, delete functions. Const map pointer, some other pointer stuff. Spin lock, sock, common socket, I guess. Or sock. We found out when we were looking at the socket in the socket video that a sock is different from a socket. Sock is essentially lower level. And then we have return types. What can we return? We can return an integer, a void, a pointer to a map value, a socket, a TCP sock, a sock common, a pointer to memory. I guess means we can essentially return anything, right? A pointer to memory or a BPF ID. I guess this is a union of these two things. Pointer to BTF ID. All right. Then we have extended return types, which are just like essentially nullable versions, I guess, except for the last one, which is a trustable version. Ref pointer to BTF ID trusted. Or I said trustable, but I think I was reading this or as or, but I think this or means both. So this means maybe null and return type to whatever BTF ID. The or means, I guess, both of them, but the optionally null is from the maybe, I guess. Then we have this eBPF function prototype, used by the verifier to allow BPF calls from eBPF programs to in-kernel helper functions and for adjusting IMM2 field in BPF call instructions after verifying. So what is this going to do? We've got a bunch of stuff. These look like registers 1 through 5. So not register 0. And I guess, what was register 0? I don't know. I want that. All right, I think I want to include Linux bpf.h. Where is it, like on 42? Remember there's a list of registers. I thought it was in the BPF header. Oh well. Did I? Yeah, I think I bookmarked this. Let's see if we can find that register list again. bpf.h, line 45. What am I doing wrong here? This is include UAPI Linux. I don't know what that means. Okay, so register 0. Yeah, this is not telling me anything interesting. Okay. So the func proto stuff keeps track of GPL only. I don't know what that means. Packet, I guess whether it has packet access, whether it might sleep. The return type, some arguments, type arg3, type arg5. Maybe this is argument arity, and you can at most have 5 arguments to a BPF function or something. And then we've got some arg_id stuff. I'm not really sure. Some argument size stuff, I guess, to keep track of, how large the thing your argument is. And a return BTF ID, the return value of the BTF ID, and a Boolean allowed. Whether something is allowed, maybe whether the program is allowed. I'm not sure. So BPF context is intentionally undefined structure. Pointer to BPF context is the first argument to eBPF programs. For socket filters, struct BPF context star equals struct skbuff star. So this is undefined, which is a little bit odd, but it's intentional. And it's going to be used as the first argument. So I guess in practice, you can pass in, they have the flexibility to change what information is passed in. And then we're keeping track of read, write, and access. Here's the register types. The types of values stored in the registers, pointer to stack, pointer to packet. So like packet stuff is pretty built in the low level, which is not surprising. Map keys, map values, sockets, TCP sockets, TP buffer. I'm not sure what TP buffer is. I guess raw TP's buffer. XDP sock. What is XDP? Express data path. A high-performance data path merged into the Linux kernel. Is an eBPF-based high-performance data path used to send and receive network packets at high rates by bypassing XDP is an eBPF-based high-performance data path used to send and receive network packets at high rates by bypassing most of the operating system networking stack. So this is like the fast path stuff, I guess. You should read this for later. We're going to bypass most of the networking stack somehow. And then it can be a pointer to mem and a bunch of other things. Okay. I'm starting to get a feel for what's going on with BPF. We've got some register state stuff. Offload operations. What's BPF offload? Is this like, I don't know if it's like hardware offload. This actually looks cool too, so I'll bookmark it. Hardware offload. eBPF with TC or XDP. So XDP is the thing we just saw that bypasses most of the kernel stack, supports hardware offload, starting with blah, blah, blah. Okay. Can I buy some hardware? SmartNIC. Is this a thing that, is this like a brand name thing? Yeah. Metronome, 50 GBE with crypto, OCP v2 SmartNIC for $50. It's like a network card, right? I don't know if this stuff is like built into most network cards now. I have no idea. Maybe if you're a hardware person, you can let me know. And then here's more offload stuff. Okay. And we've got some trampoline stuff. BPF tramp image. It's kind of a funny name. Different use cases for BPF trampoline. Replace NOP. Replace NOP at the function entry, kprobe equivalent. Replace NOP at the function entry, kprobe, blah, blah. Replace direct call instruction anywhere in the function body. I don't know what NOP is. And we've got a bunch of stuff, trampoline image, etc. BPF trampoline. Let me see if we can find NOP code. Okay. Computer science, a NOP or no-op or NOOP is a machine language instruction and its assembly language mnemonic. That does nothing. Okay, so it is a no-op, but the assembly language mnemonic version of a no-op. Then let's verify what a trampoline is. Yeah. I know what that kind of trampoline is. In computing. In computer programming, the word trampoline has a number of meanings and is generally associated with jump instructions, moving in different code paths. In low-level programming, this is where we are now, trampolines, sometimes referred to as indirect jump vectors, are memory locations holding addresses pointing to interrupt service routines, I/O routines, etc. So these are things like interrupt routines, I/O routines that are going to execute a lot, I guess, and that's maybe where the image of a trampoline comes from. Because there's going to be a lot of bouncing. There's a lot of bouncing all the time, and that might be where this image comes from. So execution jumps into the trampoline and then immediately jumps out or bounces. There you go. Hence the term trampoline. I should have read the next sentence. It's going to have many uses. Trampoline can be used to overcome the limitations imposed by the CPU that expects to always find vectors in fixed locations, and something about booting symmetric multiprocessing. And then high-level computing, you see the word trampoline in functional programming, and I always assumed that the two terms were the same, but I guess the internet is telling me that they're different. So let's see what is going on with the high-level trampolines. As used in some Lisp implementations, trampoline is a loop that iteratively invokes thunk returning functions. So it invokes functions, and these functions are returning thunks, continuation passing style. A single trampoline suffices to express all control transfers of a program. A program so expressed is trampolined, or trampoline style. Converting a program to trampoline style is trampolining. Programmers can use trampoline functions to implement tail recursive function calls in stack-oriented programming languages. Okay. So something about continuation passing. And this is the rest of the BPF header. And I'm getting the sense that I don't really need to know the rest of this. But I will scroll through it just because sometimes stuff will surprise you. More stuff on trampolines, ring buffers, checking whether programs are compatible. Program map are compatible, I guess. BPF event output, BPF program array item, an array of programs to be executed under RCU lock. Typical usage, the return value is going to be run this array. The structure returned by BPF, blah, 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 whatever this function is, should be populated with program pointers, and the last pointer must be null. So I guess this is execute a bunch of stuff one after another, but do it under the same lock, so you're not, for efficiency maybe. So that we've got this thing: to avoid allocating empty BPF prog arrays for C groups that don't have BPF program attached, use one global BPF empty prog array. It will not be modified. The caller of BPF prog array alloc. Okay. BPF prog run array. I initially read this as run away. And we've got this sleepable thing. Okay. Cool. All right, so I think that's good. Where are we? About an hour and 30? Give me a second. Okay, so the rest of this stuff, I think we're about an hour 30. I think we've actually seen most of what I want to see, except we haven't seen the just-in-time compiler. So we're going to look at the just-in-time compiler, and then I'm going to quickly plow through all the remaining open BPF files. And I think that will be a pretty solid first pass. At least I've gone from not knowing really anything at all about BPF to feeling pretty oriented as to the internals for things like verification. I mean, about as much as you can within an hour and a half from starting from little to nothing. So I'm feeling pretty good about that, but I do want to see the just-in-time compiler. And I want to at least, pass my eyes over these other files, mostly looking for things that are really salient, things that really stand out. But at the level of analysis that I had articulated at the beginning of the video about what I wanted to see, I think that there's not a whole lot of unexpected stuff. But obviously there's stuff higher in the stack that we can always learn more about. We're not really in a position to program a BPF program at all, for example. See if I can find, these are all the C files, I think, for the most part. What I want is the JIT compiler. Here's BPF pointer, local storage, LSM, malloc. Here's the verifier, which I already looked at, right? Yeah. Here's the BP filter. Yeah, you're truncating the directory. You got to do what you got to do, GitHub. You serve a lot of files and folders and stuff for free. Okay. It's not here. The JIT compiler was in like net. I'm not sure if we got a header at all. But there's at least the C file, right? And it was not in net. It was in kernel, maybe? But not in BPF, right? I guess the JIT compiler is per architecture. Is JIT in here? I want okay, so we've got JITs for like PowerPC for RISC for whatever S390 is, and ARM64. I thought we got it for AMD for x86. Let's go to ARM64 and see if we can back out. You go to x86, and then do we still have that other buffer? Maybe net BPF. Yeah, BPF JIT compiler. Okay, let's look at it in Emacs. 2,000 lines of code. That's not so fun. So we can emit code. It's going to take a pointer, some bytes, and a length. If length is equal to 1, we're going to set pointer to bytes. If length is equal to 2, we're going to do some set pointer to bytes with something like casting as a U16 thing. And similarly with the U32, except we've got some sort of barrier. And then we're going to return pointer plus length. I guess so that somehow encodes the code. Maybe the bytes thing has the code in it. We've got this emit, which is going to do program equals emit code, program bytes length while 0. So it's going to run in a loop and emit codes. Where is it getting prog bytes in length? I'm not sure. Maybe these are just variables in the scope, and as you change them, it's going to continue to emit stuff. And emit 1 B1 is just going to take B1 as the program and emit 1 byte. And emit 2 B1 B2 is going to do this thing with we're going to add B1 and B2 and left shift by 8. And that's going to be the program argument. Oh, sorry, that's the pointer argument. Yeah, ultimately the argument is a pointer. And we're going to say the number of bytes is, wait, where are we? Emit 2. Number of bytes is 2. Okay, so this is some, I don't know exactly what it's emitting, but I am guessing, since we're just in time compiling, that the thing that we're emitting is the compiled code. We've got some Boolean functions about essentially predicates, whether we are sim2, um2. I guess emitting a move dest or source file. This must be assembly. Is there some sort of like a assembly cheat sheet? Once long ago, I read a book on assembly, and then I've promptly forgotten everything about it. I'm pretty convinced that MOV is an assembly instruction. MOV, move, okay, from source to destination. So this is emitting an assembly instruction. So this is not unexpected for JIT compiling. So we're emitting assembly as you would expect from a JIT. I guess the next thing, now that we know kind of what we're doing, I want to see how it takes a whatever a program is and compiles it. Or maybe I want to see, it makes some decision about when to compile things. Maybe everything is just in time compiled. Maybe things are only just in time compiled if they're executed a lot. I don't know. The following table maps BPF registers to x86-64 registers. Okay, all right. This is pretty important. The x86-64 register R12 is unused, since if used as base address register in load store instructions, it always needs extra byte of encoding. Okay. Wait, do I not have? Okay. All right. So what do we have? So we've got some BPF register 0, I guess, is racks, which is presumably x86-64 register 0. So your racks, RDI, RSI, I guess these are just x86 registers. And we have reg to pointer registers. Something that registers and offsets and pointers is ereg is true if the BPF register reg maps to x86-64 R8 to R15, which need an extra byte of encoding. And then the other registers have a simpler encoding. R8 to R15. So I guess whenever they went from having 8 registers to 16, there's some hack about an extra byte. And by them, I mean Intel or AMD or whoever did that. JIT fill hole takes a void area in an unsigned int size. It's going to call memset, setting OXCC. So the whole space with int3 instructions. What is int3? Int is an assembly language instruction for x86 processors that generates software interrupt. Okay, so this is an interrupt instruction. It takes the interrupt number, formatted as a byte type. Int3 instruction is a 1-byte instruction used for use by debuggers to temporarily replace an instruction in a running program in order to set a code breakpoint. So this is a debug instruction that we're going to fill everything with. I'm not sure why, but I'm sure it's useful for some reason. You can add 2 registers, encode destination register and source register registers into x86 opcode byte. So this is just some computation. We have a JIT context struct, a cleanup address, epilogue code offset. I guess epilogue is maybe the thing that runs afterwards. And some program-specific offsets of labels in the code. These rely on the JIT doing at least 2 passes, recording the position of the first pass, only to generate the correct offset in the second pass. Okay. We can push callee registers. We can pop callee registers. We can emit a prologue. Emit x86-64 prologue code for BPF program. Some stuff about tail calls while jumping to another program. And we get BPF trampoline can be made to work without these knobs, but let's waste 5 bytes for now and optimize later. Okay, I guess it's harder to make it work without these stuff, but looks like there's some possibility for optimization there. We can emit a patch, which takes a program and a function and an IP. maybe some kind of pointer, maybe, I don't think it's an IP address and an opcode. Instruction pointer probably. And I guess we're going to patch stuff. Whatever that means. Maybe that like, maybe you've got some compiled stuff already and you're going to recompile it in some more efficient way or something. Emit jumps, emit RSB calls, text poke, emit indirect jump, which takes a program. And it's going to, I guess, return an instruction pointer, or is it returning the program? I'm not sure. Let's see what I mean, yeah, so the last thing it does is set pprog to prog. We're creating a prog. I'm just going to look at this because I don't think we've looked at one of these yet. We'll check if some CPU features are enabled, including something about fences, and emit two things for ret pollines. Else if, how is this different? So this is, okay, lfence versus red polline without lfence. So what's the base case? If none of the red polline stuff is configured, they're going to emit to oxff, which is, I guess, a jump instruction, to whatever oxe0 is, plus register, so whatever's in the register, which is this, okay, so this is emitting jump to %reg, I guess. And if is enabled, blah, blah, blah. We might emit some more stuff for red pollines. And then, so emit's being called here. Then how is prog actually being updated? So we might pass it into emit jump in the red polline case, but if we're not in the red polline case, how is emit actually changing stuff? Let's look at emit again. So emit has a return value. We're going to return pointer plus length. So we're changing the first argument for emit code. Oh, okay. So here we go. Yeah. Okay. So this emit all caps define thing is changing prog, whatever prog is. And so when we call it, it's overriding this prog thing, which I guess is in scope. So we're not like explicitly returning stuff. So here's another example. So we're going to set the prog pointer to pprog. And then emit is going to like send some stuff to prog, which used to be pprog. And then we're going to set pprog to the new prog. And that's what's going on. Okay. Then we can emit prolog, emit patch, emit call. Okay. Emit. So lots of emitting. Here's some generating some code about tail call indirect tail calls, I guess. I'm sure this is especially fascinating if you know assembly. Or maybe if you know assembly, it's not the least bit fascinating, and this is all like old hat and the most boring thing ever. But I feel like I still don't know where, like, how is the translation happening? Is it just like a one-to-one translation, or does the JIT compiler need to know about the structure of code? I would think that it needs to know about the structure of code. But you know what? Actually, this is just the API. Yeah, okay. So based on where we are, we're in x86 net Arch x86 net. So this is maybe just the interface, the implementation of JIT stuff. So maybe this doesn't have the code that would do like JIT optimization necessarily. It's just when you're on x86 and you call emit whatever 3vex, this is just the file that says we're going to implement it in this specific way for x86. So I'm just going to guess. I'm going to stop trying to look for optimizations. We have optimize or hide var, but I think this is kind of optimizing just the emission phase. But I think this is just emissions all the way down, maybe. Here's an interesting program. BPF prog, BPF int JIT compile. Maybe I'm wrong. Let's look at this. Is there anything above it? All right. So we're going to this might be the function that I just said may not be here. So BPF int JIT compile. I don't know what int means in this context. Maybe probably something to do with integers. But you're going to pass it a BPF program, which is prog. We're going to create some binary headers, more binary headers. A temp and an initial. We're going to set temp and original prog both to prog. We're going to create a struct for some just-in-time data. Keep track of the program length. Have a context. Some stuff about whether it's blinded, whether we need an extra pass and padding, and whatever RW image, some address stuff, and what pass we're in. I guess I think they said we needed to do 2 passes, and some counter variable presumably. So if we've not requested JIT, then we're just going to return the original program. But we've allocated all this stuff. Why not just do this first? I have no idea. Maybe just for readability. And then some stuff about blinds. We might want to blind constants, I guess, and we'll set temp to that. If blinding was requested and we failed during blinding, we must fall back to the interpreter. Let's look at what blinding is. I don't know if it's an eBPF thing. Hardening hostile code in eBPF. Constant blinding, yeah. All right, I'll read this. This is from, I guess, Samsung. Constant blinding in JIT. The JITted memory is a common target for an attacker to place an arbitrary gadget, for example, a syscall in user space. One popular technique is to encode a desirable sequence of instructions as part of immediate values, as x86-like CISC architecture provide a way to encode long bytes into one instruction. Constant blinding, also known as constant folding, is a technique to break immediate values, avoiding the use of attacker-chosen constants in the executable region. It's worth noting that there are numerous other techniques, etc., etc. Okay. And I guess this can be used perhaps to prevent Spectre. In non-privileged BPF programs, the JIT engine applies mitigation schemes against microarchitectural side channel attacks such as Spectre. And I think we saw this because that's what the red Pauline stuff should be, right? Did I bookmark this? Okay, so red Pauline. Yep, redirects to Spectre. On January 2018, Google detailed a new technique in their security blog called Red Pauline, a portmanteau of return and trampoline, which can overcome the Spectre vulnerability with a negligible amount of processor overhead. It involves compiler level steering of indirect branches toward a different target that does not result in a vulnerable, speculative out-of-order execution taking place. I guess we might as well read this blog thing again. I think I read it when it came out. What? A novel software binary modification technique that prevents branch target injection. So this is the blog. Maybe I should read the paper, but whatever. So red booleans are there to prevent Spectre style attacks, which is what I thought. But we're seeing some of that in the JIT compiler, which is, I think, pretty fascinating. And blinding is, I don't think blinding is for preventing Spectre style attacks per se. It might be. I don't know, but I think those were two separate paragraphs in that Samsung blog we were reading. But at any rate, blinding is used to prevent, to make it harder to do malicious behavior by somehow, whatever blinding or folding is, but somehow changing the thing that the attacker passed in, and not just kind of like executing it willy-nilly. And at any rate, we might do some blinding. We'll look at the auxiliary data, and if we don't have it, then we're going to allocate some data. And if we don't allocate data, then we're going to go to out. I guess we failed. And then we're going to set auxiliary data to the empty data, I suppose. And then we're going to get the addresses, check if we have the addresses, and do some stuff. Alloc an array of the addresses. And I guess do a first pass, maybe. Before first pass, or maybe not yet. Before first pass, make a rough estimation of addresses. Each BPF instruction is translated to less than 64 bytes. Okay, so we're just iterating over the program length and adding 64 and setting address at I to that program length. Okay, and then we've got the context cleanup program length. Context cleanup address program length. I guess the cleanup address is at the end of the program. Is that what that means? And here's a label, I guess. This is something you can go to. Skip init adders. And JITted image shrinks with every pass, and the loop iterates until the image stops shrinking. Okay. So I guess as we go through, we're going to optimize some stuff or whatever. And if two passes in a row have the same number of bytes or bits or however we're counting it, then we've decided that we can't optimize anymore. I don't know if it's proof that you can't optimize anymore, but I guess you're stuck with whatever optimization algorithm you're using. Very large eBPF programs may converge on the last pass. In such case, do one more pass to emit the final stage. May converge on the last pass. I'm not sure exactly what that's saying. Is last pass supposed to mean when it stops shrinking, or the pass after it stops shrinking? I don't know. So we're going to start. So pass is going to keep track of the number of passes we are, kind of like a counter. And while we're less than max passes, or image, then we're going to do pass plus plus. If no padding and the pass is bigger than or equal to padding passes, we'll set padding to true. And then program length will be do JIT of all of the stuff that you need to do the JIT. And if program length is less than or equal to 0, I guess this is, and then we go to out image. We'll set the image to null, and so if the program length is less than or equal to 0, so it's 0. I'm not sure what do JIT returns, but so let's assume that this is a sensible thing for it to be 0 or less. So image will be null. Check some stuff about the header, I guess, and maybe free stuff, copy stuff, and then free other stuff, and fall back to interpreter mode. I guess, okay, we'll set program to the original program. If there's an extra pass, we'll set the BPF function to null. We'll say that we haven't been JITted, and the JITted length is 0, and then we'll go to the out addresses. That's kind of like, that seems like an edge case. So program length should probably not be 0. If image, I'm not sure what's in the image variable, but if image is, I guess, non-zero, then program length, we check whether program length is different from old program length, which I guess is an error. Otherwise we break. And if the program length is equal to the old program length, this is, I guess, the case where we've converged. Then the number, and then we get this this comment: the number of entries in X table is the number of BPF LDX instructions that access kernel memory via pointer to BTF type. The verifier changed their opcode from LDX or mem or size to LDX probe mem size to make JITting easier. The number of entries in the X table is the number of BPF LDX instructions that access Linux kernel memory. Okay. And something about the verifier, they've changed some stuff. Their opcode from whatever this is, LDX, I guess, then mem, then maybe concatenation, LDX, then mem, then size, to LDX probe mem, then size to make JITting easier. Sounds like the verifier people made a change to help the JIT people out, is what they're saying. So we've got this exception table thing and some alignment stuff. X table, I guess that's what X table is, maybe exception table. We're going to allocate memory for the x86 instructions and X table by calling BPF JIT binary pack alloc. We'll check if we have a header. If there's no header, then prog will be equal to original prog. We'll leave. I guess header is the thing that comes out of the binary pack allocation. Otherwise, we have a header. So this is error condition. If error equal nil is basically in Go, then but if we're in the success condition, then we're going to call prog auxiliary X table and set it to whatever image is and round up program length, I guess, to the alignment. And they'll say old program length is now program length, and cond reschedule, maybe conditionally reschedule another pass, perhaps. And if BPF JIT enable is bigger than 1, we're going to call BPF JIT dump on program length proglan pass plus 1 in image. Maybe image is the thing that contains the assembly code. And if image, we check if the program is a function or we need an extra pass. I think it is the assembly image. So if we have some assembly stuff, but the program is a function, or the program is not a function, or for some reason we need an extra pass, then we go into this block, and it says the BPF JIT binary pack finalize fails in 2. And I just disconnected and reconnected, and I got a message from Jennifer Greenwood. She says, "Hi there, I'm intrigued by your channel. Can you tell me how you might use the information you share here? I felt drawn to what you were doing here." Thank you, Jennifer. I appreciate that a lot. Can I tell you how I might use the information I'm sharing here? I guess so. I don't know how to interpret that question. So the main thing that I set out to do was I was working on some stuff. Hi. I was working on some stuff, and I started reading a bunch of source code because I was having to debug a lot of stuff. So I just started reading open source projects, and I always thought it would be fun to have to be able to watch content like this. And so what I started out doing was just kind of like recording my process of like looking at things that that I thought I was going to need and stuff I was working on, and then over time I started throwing in like more kind of like whimsical different stuff. So I'm not sure if there's like really a purpose, or just like this is an activity that I thought was interesting and fun. But that being said, I think as I've gone on, it's developed more of a purpose and more of a direction. And I think part of that is just kind of making the world more comprehensible. If you're a programmer, there's always lots of stuff you deal with that no matter which side you're on, if you're on like if you hack on kernel stuff, then typically there's a whole world of like, maybe JavaScript stuff is like foreign to you or vice versa. And so just kind of trying to make the world of open source just more intelligible and available to people. So I guess um, that's the only real sense right now in which I plan to use this information, other than just developing the skill and like sharing the idea of using code and trying to figure your way out of things. And she's saying, thanks. There's a reason I was here. Oh, good. I'm glad. And she said that I used the word, yeah. I always thought of it as archaeology. Like when I think I've shared before that I started kind of doing this sort of thing, like not verbalizing my thought pattern, but kind of poking around like this at Google, because they have very good code search tools and they've got a very good, a very long history of like all of the internet things. And so you can like go back to commit one, or you don't have the first commit for like the search engine or anything, but like the first commit of the whatever iteration now they're on. And that goes back to when, some of the household names were working on projects and stuff. And so I thought that was interesting. And so I just kind of carried that over here. Yeah, I'm an interpreter. I'm just trying to figure out what's there. There's like some history to some of this stuff, like Linux. I find out yeah, cool. Do you know anything about ancient languages? Have you studied ancient languages at all? And similar to learning French. Yeah, it is similar to learning French. So I'm learning to use ChatGPT and Midjourney to streamline my. Yeah, interesting. How do you use Midjourney? That's interesting. Sumerian. Oh, really? I don't think I've ever known anyone who knows Sumerian. I took like Latin, I think, if that counts as an ancient language. Sumerian. I'm actually going to look up Sumerian now. Is an E? All right. Do I see? Yeah, I do see it. Is it like a flower? It's an A. From Sumer. I guess the Sumerian language. Around 2000 BC. That's like way before Latin, right? And it looks like hieroglyphic. Does this count as hieroglyphics? Oops. Logosyllabic cuneiform. It's a lotus. Awesome. Irving Finkelberg. Cool. Yeah, it does kind of look like code. I think that, like, I think there's something interesting to be said about languages and alphabets and information theory. And if you go back, like the story of the code breakers, what's his name? Alan Turing worked on code breaking, I think during World War II at Bletchley Park or wherever. And a bunch of the people that we associate with the beginning of computers were kind of involved in similar things. But if you also look at like some of the stuff, like the guy who cracked, I think, like linear B, there's like a very information theory flavor there. I don't know if anyone's like written anything about like understanding ancient languages and the kind of the intersection with computer science, but I think there's like a non-trivial amount of stuff there. Oh, but beyond a hieroglyph is before words, but after glyphs. Interesting. That's cool. Well, welcome. I'm glad to see you here, and I'm glad you're enjoying what we're up to. Let's see if we can figure out anything more about the JIT compiler. So where were we? We're like okay. So if we have an image, and we might do some more stuff. I guess we're going to set addresses. We're going to set the JIT data with whatever the local variables are, and then we're going to take the program BPF function and set it to a void star pointer of the image. We'll say that we've been JITted. I'll say that the JITted length is program length. And if we don't have an image, is that where we are? Then program is just going to be original program. I guess somehow, if we don't have an image, assuming an image is this assembly thing, then we've failed to produce anything useful by JITting, I guess. And more not image stuff, etc. And then we're going to turn program. Where did we do the second pass? I think we saw that, right? Or extra pass. If we have an image, we might do an extra pass. And the pass is, I guess, either way, whether we're in the error condition or not, we're calling JIT binary pack finalize. And so I guess that's the second pass. And then we might do a tail call direct fix up. And so the two things I guess that I want to make sure I look at is BPF JIT dump. And then there was something that was called like do JIT or something. Do JIT. See if we can find do JIT. Here's do JIT. It's going to take a BPF program, some addresses, all that stuff. And it's going to return an int. Allocate a bunch of stuff. We're going to detect register usage. Check about tail call reachability. Emit the prolog. Push callee registers. Keep track of length. Check something about whether we have an RW image. Then we're going to iterate over the instruction count. Allocate some stuff. Then we're going to switch on the instruction code. And if it's a bunch of these ALU codes, then we're going to maybe admit mod. Right? Let's ignore ALU. This looks like the main thing, which is what I was looking for. I guess ALU is like everywhere. How about something simple like the speculation barrier? So this might be for speculative execution specter prevention. So if the code is a BP, so this must be a BPF code. It's called BPF ST, or a BPF no spec. And we're going to emit elfence. And so this is the big switch statement that I guess is translating BPF stuff to x86 assembly stuff. But mostly, so these functions might have like some conditionals in them, but some of this stuff is just literally one BPF opcode comes in, and yeah, opcode, I guess we can call it, and then one x86 opcode comes out. I'm not sure if opcode is the right word here, but yeah, okay. So this is what I wanted to see. I'm not gonna dig into all of it, but here, where are we roughly? Line 1394. It starts, much higher, but somewhere around like 1300 lines maybe is where we get this big thing that's going to tell us how we're translating the BPF function to x86. Cool. I haven't seen yet anything that does much optimization. So I'm not sure if it's an optimizing JIT compiler. Maybe BPF is limited enough already that's not needed. If you have something like Java, I think that or Ruby, I think both have optimizing compilers or optimizing JIT compilers. I'm not sure. I don't see that yet here, but I also haven't looked at every single line of code. I don't see the word optimization much. I mean, there is some stuff where but I don't see like what you would think of as like compiler passes where it like fundamentally might change the program you passed in to another program that has the same behavior but is faster in some sense. Okay, so that's the JIT compiler. I'm glad we looked at it, and now I'm just going to try to like plow through what we have remaining, and I'm going to kind of aggressively close stuff out. Where are we? We're about 2 hours and 11 minutes in. I was hoping we could keep this under 2 hours, but that's not bad so far. Let's look at BPF filter header, since this is pretty fundamental, it seems like, now that we've looked at the rest of the stuff. So we've got things like, oops, I'm not in Emacs anymore, am I? But I can't do that. Okay, so we've got things like setting sock options, UMH ops, whatever that is, mutex locks. I guess this is not so fundamental. Mostly about sockets and whatever UMH is. You think we'll find it on the internet? I don't know. Okay, we'll ignore that. It says here's a BPF pointer, kernel BPF pointer, copying pointer from offset. That's not so exciting. Here's BPF types. Maybe this is what I was thinking of. So program type sock filter, SK filter, whatever LWT is. There's stuff about BPF events, some C group stuff, map types, and socket. Okay. Some stuff about links, perf events. Yeah, so you should be able to use BPF for like perf monitoring, which would be really interesting. Here's a header for trace, which is just going to include the XTP thing and I guess do nothing else. Memalloc. I guess I don't think that's going to be so interesting. Linux security module. I'm just curious. So this should just be the API, right? Because we're in the header. How big is it? 83 lines of code, so not much. We've got LSM verify prog. So it's going to verify something about the LSM prog. That's probably pretty interesting, but I'm going to resist the temptation to look at that just in the interest of time. We've got some inode storage stuff, some C group shim stuff, and more inode storage. So C groups, inodes, and whether LSM is trusted. I guess probably if it maybe if it came from the kernel in the first place, and verify program. And you know what? I am going to look at this. See if you can find it. I'm just going to look quickly at it. Oops. I think it's called LSM verify something or other. BPF LSM verify prog. Should be able to find BPF LSM.c. Here we go. Oops. Okay, so it doesn't do much. It checks some GPL compatible. It checks if the BTF ID contains some LSM hook stuff. Oh, GPL is the GNU public license. Oh, okay. So if it's not GPL compatible, we return saying LSM programs must have a GPL compatible license, I guess because the kernel's GPL and you're like patching the kernel code. And if you don't contain LSM hooks, whatever this attached BTF ID thing is, they're going to log and say that attached BTF points to the wrong type name. And they're going to return some sort of error number. Otherwise, we return OK. So verify prog just checks the license and checks what whether the attachment points to LSM stuff. It's a pretty quick check. This, I think, is the same header. Local storage, I guess, is not so interesting. We'll ignore that. Lurk, I don't even know what lurk is. Lurk prog attach. Do you even know what lurk is? Linux infrared remote control. BPF lurk. This can't be remote controls, can it? To raw IR. Raw infrared? I have no idea. Maybe this is like raw sensor stuff, which is actually pretty intriguing. IR decoding with BPF. Or is it intermediate representation? Yeah, look at this. A new feature was merged to allow infrared decoding to be done using BPF. Infrared remotes use many different encodings. If a decoder were to be written for each, we would end up with hundreds of decoders in the kernel. Okay, so currently the kernel only supports the most widely used protocols. Huh, fascinating. Okay, so infrared decoding, I guess. You can put your decoder in BPF so that you don't have to add it to the kernel. So I don't need this cheat sheet anymore. And I don't think I'll leave this open. No, I'll close it. Okay, and then are we just down to this one Firefox thing? Okay, here's one. Let me move the chat out of the way for just 1 second. This is just ChatGPT. Or launch. Okay. So this is this Firefox frame of just C files, and we'll just kind of close them out. This is going to be an LRU list, and I don't think we need to look at it. Whoops. Just close the chat. All right, LSM. This is Linux security module, the C function. I mean, the C implementation file. List of LSM hooks that should operate on current C group regardless of function signatures. How big is this? 376, so not much. So we'll just kind of see what's here. We've got some hooks. We've got some socket option stuff. We've got some C group stuff. We've got this verify program, which we already looked at. BPF call to. Mask for all currently supported BPM option flags. What is BPF call to? It's going to take some option set, a Linux bin program, maybe a BPRM U64 and flags. Look at the flags and maybe error out. And then we'll set BPRM secure execute to flags and BPFF BPRM secure execute. I have no idea. So Jennifer is saying, thank you for chatting. I would say that you are an archaeologist, treasure hunter, and interpreter. I'll check back. Curious if you ever find anything special things in there. Thanks so much, Jennifer. Thanks for chatting with me, and thanks for stopping by. And I hope to see you again sometime. So whatever BTF ID single is, okay. I guess we can mostly ignore this. We have this LSM is trusted, which just looks if some field is set, I guess. Struct opts. I'm gonna, I guess, just kind of ignore this. There's a talk. There's a bunch of great talks on eBPF, which I probably should have mentioned before I started this. I'll put. Most of them are linked on the. Well, not most of them, but there are some great talks on eBPF that are linked from the eBPF site. Among them is a couple of talks about the way that Google uses eBPF for security, and they use some of the LSM stuff that we just looked at. So that's interesting, but it seems like the code file is just kind of exposing functionality in hooks and stuff. Whatever this thing is, we'll ignore it. Task storage. I think we'll ignore trampoline. I don't think that we really. Yes, I guess we'll ignore it. Stack map. I guess we'll, there's maybe not so important. Map in map. Let's look at map in map. Map meta alloc. Map meta free. Okay. I don't know. Maybe this is a map that has a map. Map in map.c. Yeah, it's got an inner map. Map meta alloc. Okay, so somehow there's an inner map inside the map, and the map seemed to be important because it seems to be part of the like public BPF API. Here's helpers. BPF call to, if kernel subsystem is allowing eBPF programs to call this function inside its own verifier ops get func proto callback, it should return BPF map lookup lm proto so that verifier can properly check the arguments. Different map implementations will rely on RCU and map methods, look up the update, delete, etc. So we have a bunch of things: BPF call 2, BPF call 3, and let's see, call 3 has a BPF map push element. Or is it the name of a function? I'm not sure. And it's going to take a map. Oh yeah, okay. So this is, I think, defining a function, and the function I think is called BPF map push element. This is the type of the first argument, which is a BPF map, and it's called map. The type of the second argument is a void star, which is a value. And the type of the third argument is a U64, and it's called flags. And we're just going to return map ops, map push lm, map value flags. So this is like the internal implementation, and this is the public implementation. And we're kind of doing this throughout the whole thing. Okay, got it. So that's interesting. This is the part where the helpers is where we're essentially exporting versions of the implemented functions so that other programmers can use them. Here's dispatcher.c. The BPF dispatcher is a multi-way branch code generator. Really? The dispatcher is a mechanism to avoid the performance penalty of an indirect call, which is expensive when red pooleans are enabled. A dispatch client registers a BPF program into the dispatcher, and if there is available room in the dispatcher, a direct call to the BPF program will be generated. All calls to the BPF programs called via the dispatcher will then be a direct call instead of an indirect call. The dispatcher hijacks a trampoline function via the F entry of the trampoline. The trampoline function has the following signature. So this is some sort of hack because it's hijacking a trampoline. I think that's enough that can be considered a hack, but it's a performance. It's a way to avoid a performance penalty. It's, I guess, committed by Intel. And maybe this is part of the mitigation of Spectre. So Intel, of course, makes chips, and they're if you're a chip maker and Spectre is a thing, then you might be concerned about the performance hits of mitigating Spectre. And so that might induce you to commit something to the Linux kernel that increases performance in the presence of red pooleans. So maybe that's what's going on. Actually, just for fun, let's play the blame game to see if there's an interesting commit message here. Introduce BPF dispatcher. Oh, this is just the same comment. Okay. All right, here's disassembly. I don't know what disassembly is going to be doing. I guess this is just like looking at the assembly, maybe figuring out stuff about it. Rev map call, print IMM type. Kind of curious, but I guess we'll leave this alone now. Oh, here's disassembly.c. So I guess I will look at it. So function name is going to take some instruction callbacks, an instruction pointer, and a buffer and a size. And I guess we're going to try to get the function name. How do we do that? Function ID string. We've got a function ID string. Where did that come from? Build. Okay, so array size function ID string not equal to. Where did the function ID string come from? Oh, we've got a map. Or not a map, but an array, I guess. The BPF function mapper. So maybe we're going to build up this thing. Okay. So we've got symbols on the left side, and it's going to return strings. And then I guess we're going to build up strings in some way by looking at the assembly code. That's pretty interesting. But we're sprinting to the end here. Here's core Linux socket filter, kernel level socket filtering, based on the design of the Berkeley packet filter. So this is kernel level socket filtering. Core.c. I guess we'll take a quick look. No hurry in this branch. Exported for the BPF JIT load helper. You can program allocate JIT L info. JIT L info. Some free stuff. BPF adds delta to im. It seems to be about JIT stuff and info stuff. Where's the filtering? Not sure. Most of BPF filters are really small, but some of them fill a page. Some rounding up stuff. Okay, so this maybe this is part of a wider thing on filtering, because it seems to be kind of about more compile-y stuff than filtery stuff. Binary packing. Yeah, I don't know. Okay, so we'll move along. Here's C group stuff. Maybe similar to the filter stuff we just saw. Maybe this is just the C group stuff in the context of eBPF, which would make sense from the directory. And then, in fact, the comment says functions to manage eBPF programs attached to C groups. So we're going to ignore this. At some point, we'll do C groups. I don't know when, but that'll be part of kind of the theme of exploring the world of clouds and containers and whatnot. Here's BTF, the BPF type format, the metadata format which describes data types. And we saw this before. It's got some ELF stuff. And I think I'm going to ignore it for the most part, but I'll just scroll through. This like show data, I guess maybe like printing, pretty, showing info about the internal structs. I'm not seeing anything super important that I feel like that we need to dig into. So I guess I'm going to close it. Here's LRU list, which we'll ignore. Local storage will ignore. ITER, I'm going to ignore. inode storage for sure. C group storage will ignore. And we looked at JIT comp already. And then we're in verifier. All right, so that's the end. Where are we? We're about 2.5 hours. So we were at about 2.5 hours. All right, so that was eBPF. I think that it's a cool project, and we saw the stuff that we had intended to go in to see, and I think none of it was really surprising. But I feel much more that if I were to use something like Cilium or some eBPF based tracing, whatchamacallit, or performance monitoring, I would have a much better sense now about what's going on. And we started with the verifier, and that was doing things like checking memory access bounds and making sure that you didn't have an infinite loop, that the program was bounded and finite, and somehow contained enough for the to be run in kernel space. And we saw the just-in-time compiler. We got a sense of how it looks at the eBPF, like bytecode, you might call it, and turn it into corresponding x86 assembly code. And similar functions and programs are going to be in the various other architecture folders, like for ARM64 or Spark or whatever else we saw there. And then we saw what seemed to be where the BPF was like defining things like objects and data structures and functions that you could use to write BPF programs. And then we kind of just briefly glanced at some of the at some of the helper stuff, and just based on the names that we saw there, it will give us a sense of like what the kernel actually supports. So there's some local storage stuff. So I guess your eBPF programs can store, can have access to some local storage. That you can attach. You can do C group stuff. You can do Linux security module stuff, and we have a sense of where all those things are laid out. So that's it for now. Tomorrow is Theme Thursday. I can't remember exactly what I'm doing, but I'll look it up. Something about LSP. Haskell language server. So tomorrow is Theme Thursday. We'll be looking at the Haskell language server. That will be our second look at a language server protocol implementation. Last week we looked at the Rust language server, and it'll also help. It'll also add additional color to the kind of ongoing theme of looking at Haskell and its implementation. And yeah, that's it. I had a good time. Hopefully you had a good time, and I hope to see you again.